All right, guys. We've been looking at Chapter 1 this past week or so, and I know the schedule's kind of gotten a little squirrely, but that's okay because when we get back, we're going to take one good day to review and go over everything to make sure we kind of got what we needed to know. What I'm going to do here is I'm going to review through this Chapter 1 stuff again pretty quickly, because when you get back, we're going to have one day, and then the next day, which will hopefully be on Wednesday, we will have our exam on Chapter 1. Now, if you remember in Chapter 1, we all started off with the lab equipment, right? The things that you need to know to be able to identify, that you're going to be using again this year, primarily in chemistry. So all those pieces of the lab equipment, you need to be knowing them, okay? That's why I sent you this copy through your email of this whole PowerPoint, so you can keep looking at them over and over again, okay? So you can get an idea of what kind of lab equipment you need to have, okay? So again, we talked about beakers, right? We talked about the Erlenmeyer flask. That's a little bit difficult because you got to remember the word Erlenmeyer. We talked about the Florence flask, which is similar to the Erlenmeyer. It's just more restrictive as far as what it'll let liquids through. We talked about graduated cylinders, how we use those to measure certain amounts of liquids. And they're graduated because they have the graduations, the markings on the sides. We talked about a gas collection bottle. Its name is pretty self-explanatory. Rubber stoppers, we know those. We stopper liquids when we're mixing things. And again, those are non-volatile liquids because you don't want to use anything that can explode or heat things up with these in them because it'll be a mess. Okay? We talked about test tubes, and basically you're performing small scale experiments inside of those. And there are different sizes of test tubes. We'll primarily use the medium sized ones most of the time. Every once in a while we'll use an ignition tube, but not very often. Test tube holder, for obvious reasons. If a test tube is too hot, you're going to need that test tube, right? Brushes to clean out your test tubes or other equipment that you're using to clean out. Okay? Pretty straightforward there. Test tube racks to hold your test tubes while you're performing multiple experiments with them, right? Spot plates, these are where we're using really, really small amounts and we're doing multiple little tests on these things just to see what kind of reaction we're getting. So we're using them in small amounts of chemicals, okay? A watch glass, remember this one kind of looks like a big giant contact lens. It's again there to hold a solid, so if you make a reaction that produces a solid, you can put it on there and let it sit for a while and dry out or whatever you need it to do. A glass stirring rod is, again, self-explanatory. Medicine dropper, absolutely. We'll probably use those once or twice, but usually what we end up using is a pipette because remember these bulbs tend to dry rot and crack, so we intend to use a plastic pipette more than we do a medicine dropper, but it's the same basic idea. Okay? We're going to use forceps from time to time to pick up small pieces of elements and materials that are solids that we can pick up with, but again, not too awful often. Funnel we'll be using all the time. And again, you know what a funnel does, it's self-explanatory there. A pipette called a Moore pipette. This one we don't use hardly ever because again, it requires a rubber stopper, but it uses this pipette to help you with measured amounts, to give you the specific amounts of liquid that you're going to deliver to the chemical experiment. Okay? A wash bottle, again, self-explanatory what it's going to do. You're basically cleaning out stuff. A weigh boat, again, self-explanatory. Spatulas are there to take and transfer solids from a bottle to what you're using them for. You're dipping them out. And remember, there's a version of that called a scupula, which is even bigger, which allows you to scoop more materials out at once. Okay? And again, the mortar and the pestle, we use these to grind up stuff, and we'll use these a couple times this year where we're going to grind up solids and make them into powders. Pretty straight. Ring stands, we're going to use a ring stand to hold up a ring and create a base platform that we're going to use with Bunsen burners most of the time. There's the iron rings themselves. They're the platform itself that we're going to put stuff on. Sometimes we'll have utility clamps of different kinds and variations. We even have some that are used to clamp thermometers, right? Wire gauze is to put on top of that iron ring so that we can heat stuff evenly and create that base. If we're putting a beaker or a flask on there, that we can lay it on top of that iron ring. Tongs, obviously beaker tongs are there to pick up a hot beaker because you don't want to grab it with your bare hands. A Bunsen burner is obviously to create fire. We're heating non-volatile liquids. A striker is used to light the Bunsen burner. We've all seen these before. If you ever had, again, shop class, you've seen these a bunch before. Evaporating dish we don't hardly ever use, but sometimes you can heat solid compounds with higher, with more stable compounds, let me rephrase that. It's basically like an evaporating dish. A crucible we won't hardly ever use again because you're heating solids to melt them most of the time, and we don't have the temperatures usually required to melt certain things anyway, so we don't hardly ever use them. But I wanted you to see them and know them anyway. The clay triangle holds the crucible in place over the Bunsen burner, so with the ring so it doesn't fall through. The crucible tongs, obviously, to pick up a hot crucible. Okay. A burette, this is, again, one that we're going to primarily use with acids and bases when we're performing an acid-base reaction. It's called a titration. We'll be using those. And I know I'm going through these pretty quickly, but we've already seen these, so we should know them. And you got this packet that I sent through to your emails the other day, yesterday. So you should already have this stuff, okay? Now, the next thing that we looked at was units of measurement. We said that we measure things based on the SI scale, right? The International System of Measurements. You called it the metric system, but there's more to it than just the metric system, whatever. Everything's based on units of 10, which is good for us. It makes everything easy to calculate, right? Now, we said that we had several different prefixes that we're going to be talking about. Some of these we have seen before. Whoops, sorry, hit the button too fast. And you can see meter, liter, and gram is our base, and then we can multiply everything by 10 to get different ones, and then we can drop down, divide by 10 to get even smaller ones. And again, this was real easy, wasn't it? Because all we had to do was convert from one another. And again, I'm going to show you what I'm talking about here for just a second. Because if I give you some numbers, here, let's see if I can pick a good color. Oh, good. All right. See if I have 35.5 milliliters, I want to know how many liters that is, right? So what we had to do was take this and go 35.5 milliliters. Milli is 10 to the negative third, right? And liters is 10 to the 0 power. Well, again, what's the difference between -3 and 0? The difference is 3 numbers, right? 3 decimal places. Now, which way are we going to move it? From left to right or right to left? Well, if you're going from a smaller, because this one's smaller, right, to a larger, because this 0 is actually larger than -3. If we're doing that, right, we got to move our decimal to the left. Okay? So if I move this thing 3 spaces to the left, and there's my decimal, I'm going to go 1, 2, 3, and put that there, so that my answer is now see? Pretty straightforward, y'all. Okay. And that's, again, how we go from that one. What if we do this, though? What if we go 127.1 kilometers is equal to how many meters, right? Well, it's the same thing. 10 to the third this time for kilo, but 10 to the 0 for meters. Well, what's the difference? Well, again, I picked 3 because it's pretty straightforward. Three decimal places, but to the right or the left. Well, we're going from larger to smaller. We're going to move the decimal to the right. In this case, we move it 3 to the right, so we go 1, 2, 3. So we go 127,100 meters. 127,000 meters. Now again, that's a very quick breakdown of the measurement movements, right? Well, we've already done this. We spent a day, about a day and a half on this, right? So we should have some idea of how it works anyway, correct? Okay. Now, we talked about measurements, right? How to read measurements. And we talked about this thing called the meniscus. Remember, water, when it is in a glass tube, it tends to stick to the sides. So you always want to read that curve from the bottom. Okay? Always want to read that curve from the bottom. Don't want to read above it because you'll get a messed up number, so don't do that. Okay? Now, we always read it not like this, right, because that's bad, but from direct angle. Otherwise, if you're reading it from a bad angle, y'all know this because we talked about this. If you read it from not eye level, not straight ahead, you'll have this thing called a parallax error, right, where things look like it's different than what it actually is. You get a bad number on there. Y'all remember we talked about driving in a car and looking at the speedometer or the gas gauge from the passenger side and how it doesn't look right, but if you're looking at it from straight on, you see what it actually is. So that's a parallax error. We have this occur if we're not careful. So we always make sure that we read them at eye level. Okay? And remember we talked about measuring volumes. So we have to measure things like certain digits, those that we know for sure that we have passed, and then the uncertain digit, just one of those, that we just estimate one number. No more than one number would we estimate, only one. Okay? So again, if we gave you this one right here, we know that we've got 60, 50, and 40s down there. We know we're at least at 50. There's 55s. Each one of these is 1 milliliter. So we know we're at 51, 52, but we're not at 53 yet. So we know we're somewhere between 52 and 53, right? We know we're at least 52 point something. Okay? So when we look at it real close and we go, okay, 52.7, right? Give or take. Now you could have said maybe 52.8, maybe 52.6, okay? So when we figure it out, that's probably what it will be, around 52.7. That last number is the only one that we estimate. The other two we know for sure, okay? Because we know we passed that point, okay? And we do the same thing over and over again, but we also do this with a thermometer, right? And again, looking at a thermometer, you read the certain digits, like this one, 87, and it's between 87 and 88, it may be halfway, right? Or a little bit below halfway, 87.4. This one right here, it's at 30, 35, and that's 40, so this is at least 35, right? And then, right, pretty much the meniscus is at the 35 mark, okay? So that's the thermometer reading. And again, you use these really simply and really straightforward, it's not a problem, okay? As long as you can read that thermometer. Because these are the kind of thermometers we're going to have. We're going to have the alcohol-colored red or green thermometers. Okay. Now, let's see here. Where we're at right now, because we skipped all that. What we then started talking about was the basics of chemistry, right? We talked about the simple stuff when we talk about chemistry. Okay. We talked about what chemistry was, the study of composition, structure, and properties of matter, and the changes that it undergoes. We talked about what matter was, anything that has mass and occupies space. We said that mass was the measure of that amount of matter that you have. And these are definitions that you have seen before a lot, okay? We also talked about atoms versus elements, right? Atoms are the smallest unit of an element, right? That has the properties of that element. And an element is a pure substance made up of only one kind of atom. Those two definition sets are basically reciprocals of each other. One answers the other one, basically. Okay? We talked about a compound where it's two or more elements chemically joined together. Right? They're bonded. Like table sugar, for example. This is table sugar. There's sodium chloride. There's sodium bicarbonate. There's a million different compounds on this earth that are formed chemically. Okay? We talked about the properties of matter, either extensive or intensive. Remember, extensive, how much you have, the more you have of it, that's a property. Like, for example, volume, obviously, mass, duh, and then something called energy content, right? Intensive properties, it doesn't matter if you got a little bit or a lot, or a huge amount. It doesn't matter. That property is the same either or. Like, for example, melting point and boiling point, right? As well as things like density will be the same no matter if I got a cup of water or a gallon of water or a tank full of water, right? It's still, these things will still be the same no matter how much I have. Okay? We talked about physical changes where you change one thing to another state. And again, these were your 4 stages: the solids, liquids, and the gases and plasma. Definite volume and shape for solids, definite volume but indefinite shape for liquids, no definite volume or shape for gases, and then plasma was that ionized gas, that was that charged gas. So these are the majority of these are the 4 main states of matter in the universe. Now again, this is what we normally see. We've seen it before. We saw it in 9th grade physical science and 8th grade physical science, and you've seen it most of your science career, right? Okay. Now, then we talked the other day before we got out about chemical changes, right? What is a chemical change? Well, it's where we're changing and making different substances. It's no longer physically the same stuff, right? It's something new, okay? And a lot of times you'll see heat and light as an evidence of a chemical change. Not always, but a lot of times you will. Like, for example, these fireworks, right? Now, then we talked about, and I gave you a copy of this, and if you didn't get a copy, we'll get you a copy as soon as we get back, okay? This copy of this graph that talks about matter and the different kinds of matter and how you can separate them. And we said, does matter, can it be separated by physical means? If it is, it's a mixture. Is it uniform in composition? Is it the same throughout? If it is, it's a homogeneous mixture or a solution. If it isn't, it's a heterogeneous mixture, which means you can see the individual parts and you can separate them out. If it does not or can't be separated physically, it's a pure substance. If you can break it down chemically, it's an element. If you can't, if you can break it down chemically, it's a compound. If you can't, it's an element. And again, I gave you a copy of this so you don't have to sit there and write the whole thing down. You can just study this. Okay? Now, we said that we can separate mixtures quite easily. We talked about dye stains, ink stains and things like that. They can be separated into the components. We talked about separating others through the process of distillation, and even talked about electrolysis. Sometimes you can use it to separate, like water, you can actually break it down in hydrogen and oxygen, okay? Just by using this setup where you're producing electricity that will allow it to separate the positive and negative sides, okay? All right. Now, the last thing that we were talking about were the different kinds of matter. There's 3 basic kinds: metals, nonmetals, and metalloids. And we said the thing that made metals metals were they were good conductors of heat and electricity, they were malleable, which means you can flatten them into sheets, and then they were ductile, which means you can turn them into, spin them into wiring. Okay? They are usually going to have a very high tensile strength, which means they don't rip apart very easily. And they also have luster. They're shiny. Okay? So metallic luster. And we gave you some examples of potassium, zinc, copper, and mercury. And most elements on the periodic table are metals. The vast majority of them are metals. Okay? Then we had nonmetals, which were the exact opposite of the metals. They, again, were poor conductors of heat and electricity. They tend to be brittle. They're not malleable or ductile. A lot of them are gases. And as a matter of fact, on the right side of the periodic table, the majority of nonmetals are gases at room temperature. They're also not very shiny. They're not lustrous. They don't have a shine to them. The solid ones don't. Okay, and we said things like sulfur and phosphorus and carbon. Now, I know carbon's shiny. It's shiny in the only sense of when it forms a diamond, it can look shiny because it's reflecting the light. Then the last group were the metalloids. Now they're in between, and again on that little periodic table you can see a zigzag right here. These elements right here are in between the metals on the left side and the nonmetals on the right side. And they are kind of the middle ground. All right? They have characteristics of both metals and nonmetals. They're kind of halfway in between them. Okay? Some of them are brittle, some of them aren't so brittle. But they're not nearly as brittle as nonmetals. Okay? We call them semiconductors, okay? Which means they conduct electricity okay. And that's actually a good thing because the last thing I wanted to mention besides that was this one called silicon. Silicon is awesome because of what it does for us. It is metallic in luster. It looks kind of shiny. It is brittle, though. It's a semiconductor, which is great for us. You ever seen one of these things? This is a computer chip. This is why we love it, because it allows us to make computers much, much smaller because of the fact that we can get all this information on one of these computer chips because of the fact that it is a semiconductor. It allows electricity to move somewhat. We can control it a lot better. And that's why we like this one, okay? There are other ones, boron and germanium and arsenic and antimony and tellurium. These are also non-metals, metalloids, okay? So again, we kind of quickly ran through chapter 1 because chapter 1 is the simplest chapter of all. I know that was short. We're going to go back over this again when we come back and do a couple things when we come back that next day, and then we're going to have a test. It's a lot of stuff, but most of the stuff is not that hard, is it? It's stuff, a lot of it that we've seen before. So if you have any questions, email me. When you get a chance, I will check them Friday and Saturday and Sunday and even Monday, okay? So if you have a question between now and then, do not hesitate to email me so that I can hopefully get back with you as soon as possible, okay?